Vector-valued functions. Here we have a curve C defined by the equations x equals x of t, y equals y of t for t between a and b. The equations x equals x of t and y equals y of t are known as parametric equations. X and y are functions of a third variable t called a parameter. As t increases or decreases, the point xy, or x of t, y of t, traces out a parametric curve C. Similarly, in 3-space, we could define a curve C by the equations x equals x of t, y equals y of t, z equals z of t for t between a and b. Here, x, y, and z are functions of a third variable t, again called a parameter. And as t increases or decreases, the point x, y, z equals x of t, y of t, z of t traces out a parametric curve C, this time in 3-dimensional space. We could describe the curve using a single equation via a vector-valued function. R of t equals the vector x of t, y of t, or x of ti plus y of tj. X of t and y of t are the component functions of the vector-valued function r. Similarly, in 3-space, we have the vector-valued function r of t equals vector x of t, y of t, z of t, or x of ti plus y of tj plus z of tk. Once again, x of t, y of t, and z of t are the component functions of the vector-valued function r. Let's look at an example. Go ahead and pause the video, try this example yourself, and then resume the video to check your answer against mine. Here we have a vector-valued function, r of t equals e to the ti plus root t plus 2j plus ln t minus 2k. The components of this vector-valued function are e to the t, the square root of t plus 2, and ln of t minus 2. What is the natural domain of R? Well, for e to the t, there are no restrictions on the domain. You could plug in any t value and get a corresponding value for e to the t. For square root of t plus 2, we need t plus 2 to be greater than or equal to 0, or equivalently, t to be greater than or equal to -2. And for ln t minus 2, we need t minus 2 to be greater than 0, or equivalently, t greater than 2. So we see that t has to be greater than 2 in order for t to be able to be plugged into each of these 3 component functions. So in interval notation, that's the open interval to infinity. Okay, another example. Here's a vector-valued function, r of t equals 2 cosine ti plus 2 sine tj plus tk for t greater than or equal to 0. Let's sketch the graph of this vector-valued function. You may want to pause the video and try this yourself before I do it. As a hint, you may want to try to eliminate the parameter using some trigonometry in order to find a surface on which the curve is located. Go ahead and pause the video and try it yourself. First, I want to note that if I take x squared plus y squared, that's the square of 2 cosine t plus the square of 2 sine t, which is 4 cosine squared t plus sine squared t. By the main Pythagorean identity, cosine squared t plus sine squared t is equal to 1. So we get 4 times 1, which is 4. This means that our curve lies on the cylinder centered at the origin of radius 2. So there's a quick sketch of that cylinder. Now let's look at a little table of values. Notice in this table that I used some easy t values to compute x, y, and z for. For example, when t is 0, then since the cosine of 0 is 1, we have 2 cosine of 0 is 2. The sine of 0 is 0, so 2 sine of 0 is 0. And since we're plugging in t equals 0, we see that the z component, which is just t, is also 0. For pi over 2, the cosine of pi over 2 is 0. The sine of pi over 2 is 1, so the y component is 2 times 1, which is 2. And the z component is just t, so we just copy the pi over 2 into the z column there. And finally, when t is equal to pi, well, the cosine of pi is minus 1, so the x component is 2 times minus 1, which is negative 2. The sine of pi is 0, making the y component 2 times 0, or 0. And once again, the z component is just t, so we copy that pi over into the z column there. Okay, so just plotting that first point, when t equals 0, we get the point 2, 0, 0. That lies right along the positive x-axis, where x is equal to 2. When t is pi over 2, we get the point 0, 2, pi over 2. So we go right 2 units on the y-axis and then move up pi over 2 units. And for that third point there, when t is equal to pi, we get the point negative 2, 0, pi. So we move backwards along the x-axis 2 units and then up pi units. Okay, so tracing out the curve as we wrap around the cylinder and hit those points, we could see we get something that looks like this. This curve is known as a circular helix. Note that the curve is circular in the x and y directions and keeps increasing in the z direction. Here's another example. R of t equals 2 cosine ti plus 2 sine tj plus 3k for t greater than or equal to 0. Notice that the x and y components are the same as the last example, but the z component is a little different. Pause the video and see if you could sketch the graph of this vector-valued function. Notice that since the x and y components are the same, then we see, just like in the last example, that this curve lies on this cylinder of radius 2. If we look at a table of values, notice that the z component is always 3. So we actually just get a circle of radius 2 at a height of 3 units above the xy plane. Let's move on to the calculus of vector-valued functions. Starting with the vector-valued function r of t equals x of ti plus y of tj plus z of tk, we define the limit as t goes to a of r of t component-wise. So we take the limit as t goes to a of x of t times I, plus the limit as t goes to a of y of t times j, plus the limit as t goes to a of z of t times k. We define the derivative of r component-wise as well. R prime of t is x prime of ti plus y prime of tj plus z prime of tk. And you may have guessed it, we define the integral of r of t dt component-wise too. The integral of x of ti plus the integral of y of tj plus the integral of z of tk. Let's try an example. Once again, pause the video, try this example yourself, and then resume the video to check your answer against mine. Okay, so here we have the vector-valued function, r of t equals e to the ti plus t cubed j plus 2 sine pi t k. Let's do the limit as t goes to 0, r of t. That's just I, right? Because the limit as t goes to 0 of e to the t, we could just plug in the 0 to get 1, so we get 1i. For the second component, we could again plug in the 0 to get 0 cubed, which is 0j. And the sine of pi times 0 is just the sine of 0, which is 0. So again, we get 0k. So the answer is just I. Now for r prime of t, we differentiate component by component. The derivative of e to the t is e to the t, so we get e to the ti. The derivative of t cubed is 3t squared, so we get plus 3t squared j. And the derivative of 2 sine pi t is 2 cosine pi t times pi. There's a little chain rule in there, so we get 2 pi cosine pi t times k. For the integral, we integrate component by component. The integral of e to the t is e to the t plus some constant, which I'll call c1. So we get e to the t plus c1 times I. When we integrate t cubed, we get t to the fourth over 4 plus another constant. I'll call it c2 times j. And for the third one, we need a little substitution. If I let u equal pi t, then du is pi dt. So we get minus 2 over pi cosine pi t plus another constant. It's good practice to combine all the constants into a single vector constant, c. For this last one here, we're doing a definite integral. We've already found the antiderivatives. We're just going to plug in the 0 and the 1. So e to the 1 is e, and e to the 0 is 1. So for the I component, we get e minus 1. For the j component, 1 to the fourth over 4 is 1/4, and 0 to the fourth over 4 is 0. So we just get 1/4 for the j component. And for the k component, when we plug in a 1, we get the cosine of pi, which is -1. And when we plug in a 0, we get cosine of 0, which is +1. So -1 minus 1 is -2 times -2 over pi is +4 over pi. Check those computations carefully so you don't mess up those minus signs. Theorem. R prime of t, even though we defined it component by component, it actually turns out to have the same limit definition as the derivative definition from Calc 1. In other words, r prime of t is the limit as h goes to 0, r of t plus h minus r of t over h. Let's prove this in two-dimensional space. The proof in 3 space is very, very similar. Okay, let r of t be the vector-valued function with components x of t and y of t. So I'll write it as x of ti plus y of tj. Then let's look at the limit as h goes to 0, r of t plus h minus r of t over h. Well, r of t plus h is x of t plus hi plus y of t plus hj, and r of t is x of ti plus y of tj. So I just replaced each of those vectors by what they are in component form. And now we can reorganize the numerator, so we get x of t plus h minus x of t over h times I plus y of t plus h minus y of t over h times j. Now, by the definition of taking a limit of a vector-valued function, we just do it component by component. So we could take the limit of each of the components. And the first component becomes x prime of t, and the second component becomes y prime of t. So we get x prime of ti plus y prime of tj, which is just r prime of t, exactly what we were hoping it would be. Let's draw a picture of this theorem. So here's the graph of a vector-valued function r of t. Let's take a point P on that curve and the corresponding vector r of t0. So t0 is the parameter value that corresponds to the point P. In other words, if we plug in t0 for x of t and y of t, we get that point P. And here's what the corresponding vector r prime of t0 looks like. This vector, r prime of t0, is known as a tangent vector. And the corresponding tangent line has equation r of t equals r of t0 plus t times r prime of t0. Note that this is just the equation of a line passing through the point corresponding to t0 when you plug it into the vector-valued function r of t0, and is parallel to the tangent vector r prime of t0. Go ahead and try this example. Pause the video and then resume the video to check your answer with mine. Find parametric equations of the tangent line to the graph of the curve C, whose parametric equations are x equals t squared, y equals t squared minus t, z equals -7t, at t equals 3. So we first will just write down the corresponding vector-valued function, r of t, which is t squared I plus t squared minus tj minus 7tk. Let's plug in the t value, which is 3. 3 squared is 9. 3 squared minus 3 is 9 minus 3, which is 6. And negative 7 times 3 is negative 21. So we see that r of 3 is 9i plus 6j minus 21k. Now let's take the derivative. R prime of t, well, the derivative of t squared is 2t. The derivative of t squared minus t is 2t minus 1. And the derivative of negative 7t is negative 7. Plugging in 3 into the derivative, 2 times 3 is 6. 2 times 3 minus 1 is 6 minus 1, which is 5. And that negative 7 is constant, so we just copy it over. And we see that r prime of 3 is 6i plus 5j minus 7k. We can now write our parametric equations by taking x0 to be 9 and the first component of the vector to be 6. So we have that x is 9 plus 6t. Similarly, we have y equals 6 plus 5t and z equals negative 21 minus 7t. Let's finish up this lesson with some product rules. The product rules for the dot product and the cross product are very similar to the product rules you know from Calc 1. The derivative of r1 of t dot r2 of t is r1 of t dot r2 prime of t plus r1 prime of t dot r2 of t. And similarly, for the cross product, the derivative of r1 of t cross r2 of t is r1 of t cross r2 prime of t plus r1 prime of t cross r2 of t. You have to be especially careful with the cross product here. Remember, the cross product is anti-commutative and not commutative. So you cannot interchange the factors in either of those terms in the final result when taking the cross product. So make sure that you apply R1, R2, R1 prime, R2 prime correctly when doing the cross product. Okay, here's one more example for you to try. Pause the video, try this example yourself, and then resume the video to check your answers against mine. So we're given two vector valued functions. R1 of t is cosine ti plus sine tj plus tk, and R2 of t is I plus tk. We want to find the derivative of the dot product of the two vector valued functions and the derivative of the cross product of the two vector valued functions. Let's do it by using the product rule. So first of all, we're going to need R1 prime of t. The derivative of cosine t is negative sine t. The derivative of sine t is cosine t. And the derivative of t is 1. Therefore, R1 prime of t is negative sine ti plus cosine tj plus k. And for R2 of t, the derivative is just k because I is constant. There's no j term, and the derivative of t is 1. So we just get R2 prime of t equals k. Okay, for the derivative of the dot product, well, we have to take R1 of t dot R2 prime of t. So since R2 prime of t just has a k component, that's just t times 1, which is t. And then for R1 prime dot R2, well, we do negative sine t times 1 plus cosine t times 0, so that goes away, plus 1 times t. And we just get negative sine t plus t. Okay, combining the two t's, we get 2t minus sine t. Okay, let's do the derivative of the cross product. So first we're going to do R1t cross R2 prime of t. So R1t consists of components cosine t, sine t, and t. And R2 prime of t consists of components 0, 0, and 1. And then we're going to add R1 prime of t cross R2 of t. R1 prime of t consists of components negative sine t, cosine t, and 1. And R2 of t consists of components 1, 0, and t. For the first cross product, we have sine of t I minus 0i. And for the j component, we get 0 minus cosine t j. And for the k component, we get 0 minus 0. So the whole first cross product is in that first set of parentheses there. For the second cross product, we get t cosine t minus 0i. And then we get 1 minus t sine t, so 1 plus t sine tj. And for the k component, we get 0 minus cosine t k. Okay, so just combining like components, we have sine t plus t cosine t times I plus 1 plus t sine t minus cosine t times j minus cosine t times k.